Hello, my name's Nicholls, Camera Sales Engineer at Quantum Design. In this presentation, I want to go through some of the different camera technologies and how they can fit in your machine vision systems. As an outline to this talk, I will firstly introduce Quantum Design as a company, and then move on to the different types of camera technologies that we offer. These go from hyperspectral, visible-SWIR imaging to thermal imaging. And then I will talk about the application areas where these fit into. And then lastly, I will summarize. Quantum Design is one of the leading distributors of high-tech instrumentation for scientific, academic, and industrial research. Our office is located in Leatherhead, Surrey, southwest of London, and we consist of a team of 9 people in sales, marketing, and service. And we're part of the worldwide Quantum Design group, which employs around 500 people worldwide and is a hybrid model of manufacturer and distributor. Quantum Design has been going for a number of years now and is a very stable company with lots of knowledgeable and experienced individuals. Just to give you an idea of our global structure, Quantum Design International is split into regions across the globe. As you can see, Quantum Design UK and Ireland is part of the European group, which consists of Italy, Germany, Switzerland and France, and covers the rest of Europe. As I said before, Quantum Design is a little bit unique in that it is both a manufacturer and distributor of products. The manufactured products are made in San Diego in the US, and they are a leader in cryogenic systems such as squid magnetometers and helium liquefiers. Our distribution products cover a wide range of areas in both academic and industrial research, from cryostats to imaging cameras, all the way to spectroscopy systems and X-ray microscopes. These products are split over a number of partners who we work closely with to ensure that we can offer our customers the best equipment to meet their application needs. So hopefully now you have a good idea of what we do at Quantum Design. And now on to the main part of my talk. And the first question we're going to ask is, which camera technology do I need? My response to a customer when they come to me with this question is, what is the problem? What is it that you want to detect? And you have to have a good idea of this. So let's say that you want to detect overcooked product. The next thing to ascertain is, what are the effects of the product when it's overcooked, or it has a certain defect, or is outside of certain tolerances? Are there visual differences in color or size? This could be detected by, for example, hyperspectral or visible-SWIR imaging. Has the product reached too high a temperature? We can then look at thermographic solutions. Has the composition of the product changed? And in this case, we would go to hyperspectral imaging. As you can see, if you've got a good idea of your problem and the effects of that problem, we can then go down into the different technologies and find the best solution. Firstly, let's discuss more about hyperspectral imaging. Here is a video from our partner SpecIm that explains how the technology works.
Hi! In this tutorial, we will introduce how SpecIm hyperspectral cameras work. There are different ways to collect hyperspectral data. SpecIm products are line-scan hyperspectral cameras. They collect full spectral and spatial information of the target line by line. Sometimes the term push broom is used for the same technology. The key components of a line-scan hyperspectral camera are an imaging spectrograph, a grayscale camera, and an objective. All these components must be optimized for the camera's wavelength range. When recording a normal black and white image, you'll need the objective and the camera. The objective projects the target to the camera sensor, where the image is recorded. To compare this with our book illustration, the result is a one-page black and white leaflet. Once the imaging spectrograph is added, we can record hyperspectral data. Let's examine the imaging spectrograph in more detail. The imaging spectrograph contains an input slit, a culminating optics, a dispersive unit, and a focusing lens. The objective forms an image to the input slit. The input slit limits the incoming information. Through it, the information passes only from a single line. Because of this component, these cameras are line scan cameras. Input slit is required to measure accurate spectra. The narrower the slit, the more accurate spectra you get. The culminating optics directs and culminates the light from the slit to the dispersive unit. With the dispersive unit, the incoming light spreads into the spectra. The focusing lens is needed to focus the image to the grayscale camera. The grayscale camera is used to measure the intensity of the dispersed light. Now we have a spectral image. In this image, every row contains intensity information from a different wavelength. Together, the rows provide the full spectrum so that each column contains the spectrum from a single location. This is how the technology can provide answers to questions what based on the spectrum and where based on the location. The image of the whole target is recorded line by line with this hyperspectral camera. This is how line scan hyperspectral cameras work. The imaged lines together provide the final spectral image that is also called a data cube. High data quality and fast operation make this technology suitable for different environments.
This technology can be used in a multitude of different ways. Here are some industrial applications. As we can see, the technology can be used in waste treatment automation. Cameras can be used online for sorting. Products can be scanned and materials identified online. Also, food quality and control, as I touched on earlier. As can be seen, this is a non-destructive process, so samples do not need to be destroyed. And various properties can be measured, such as parasites, protein, moisture content. Lastly, colour quality. As you can see, this is a non-invasive process, so there's no damage. The applications of hyperspectral imaging are wide-ranging, from colour analysis and food sorting and detection of foreign objects online, even to detection of film thickness for transparent objects such as semiconductors or plastics, and many more. Now to discuss thermal imaging. How does it work? There are three modes of heat transfer. The first being conduction, which is heat transfer within a solid object. So if we heat one end of a metal rod, the heat is transferred to the other end of the metal rod. This is how a thermocouple works for temperature sensing measurements. The next is convection. This is heat transfer within a liquid or a gas. So the gas heats up, can rise and warm up the other part of the gas. So this is transferring the heat. The last is radiation. So for this, there is no transfer medium. Hot objects emit electromagnetic radiation, and this is given out to the environment, and this can be absorbed by other materials, so the heat has been transferred. This is how, so radiation is what the temperature measurements are based upon for thermal imaging. So as I said, the thermal imaging camera works out the temperature of objects in the image by measuring its radiation. So what's the science behind this? So if we go to Planck's radiation law, we can see the graph plotted here. This is emission from a so-called black body. So this is a perfect emitter of heat radiation. we see that in this graph we plot emittance against wavelength, and if we look at the peak of these different curves, so the dark blue, so this is the emission from a black body object that is at a temperature of minus 196 degrees Celsius, and we see the peak is way out in the infrared at about 14 microns. If we warm up this object to be at 0 degrees, the peak is around 10 microns. And if we warm up further, the peak of this emission ends up around 3 microns, and so on, going all the way from the IR and into the visible. So the peak of an object at 6,000 degrees Celsius is in the visible wavelength range. So this is when things glow hot. For most everyday applications, we see that if we're below about 1,000 degrees Celsius, we want to be looking in the infrared range and into the mid-wave and even long-wave IR. So this means we need a different type of detector to detect radiation in these wavelength ranges. These detectors are generally MCT or indium selenide based detectors. One industrial application of thermal imaging is metal sheet pressing. So here we have a system where metal sheets are heated and then they're pressed into a certain shape and then taken off to be examined. So here we have 4 measurements of temperature, so out of the furnace, before pressing, after pressing, and the cooling process. So what this can give us information about is detection of defects before and after pressing, also any uneven heating in the furnace process, and also gives position information for other devices in the system to adjust position. Thermal imaging also has a wide range of applications, from additive manufacture to measuring dynamic thermal processes in manufacture, and also analysis of electronic components. So here you see the heat distribution across a PCB, so you can determine if there are any areas where parts may fail or melting may occur. Also, one application is non-destructive testing. Here at the bottom you see a part. This is a piece of carbon fiber, and we use non-destructive testing where a pulse lamp is placed on one side of the sample and the camera on the other. This causes heating, pulsed heating. The camera, using some algorithms, non-destructive testing algorithms, can detect any defects that may be within the material, such as inserts, cracks, or impact damage, such as we can see here. Lastly, just to discuss visible and shortwave IR imaging, infrared cameras can be used anywhere where there's difficult lighting conditions, such as too high or too low light levels, or when imaging objects that reflect or emit a large amount of visible radiation. Apart from visualization of objects, infrared cameras can be used to look at defects in certain materials, as shortwave infrared light can penetrate into such materials like semiconductors, plastics, and even visualize bruising in certain fruits. Our partners are Raptor Photonics with their OWL640T camera won Best in Machine Vision at the 2021 Vision Systems Innovator Awards. The OWL640T offers high resolution with VGA output and 10 micron pixel sizes. The sensor is also optimized through the visible and shortwave IR with broadband detection range from 600 nanometers all the way up to 1.7 micron. So I've given you an overview of 3 machine vision camera technologies, so hyperspectral, thermal and shortwave IR imaging, and I hope you have a better idea of their potential applications and areas where one technology may be used over another. So whether you want to do quality control, detect foreign objects, damage in your sample, burning of foodstuffs. I hope you know which technology to start looking at. And of course, hopefully this is just the start of our conversation, so you're welcome to contact us at Quantum Design. We do various webinars, online demos. We can set up a meeting where we can discuss your application in more detail and see how we can help you. You can also learn more on our website. There's various materials there for certain applications for you to discover. And you're welcome to drop us an email either at our info address or to me personally, and I'm happy to discuss your application and find you the best solution. Thanks for listening.